So we're in your chemistry book, chapter 6, section 2. We were talking about thermodynamics, and now we're going to be talking about the heat in chemical reactions. We're going to talk about the word enthalpy. Enthalpy is a new word for you, but don't let that get you confused because it's very close to energy. But the energy is a little different because the energy also is going to be affected by pressure and volume in the midst of the surroundings area where the energy is. So you're going to be taking in the equation of enthalpy, you'll be taking H being the word enthalpy, which means all the energy in an internal system. It's kind of hard because you think, oh, is that heat? Well, heat is part of it, yes. But enthalpy is all the energy in the internal system plus which would be all the energy, regular energy, plus pressure and volume. So it's important to know that, and the changes of that, as I go here, I'll show you the changes here. This is the change of enthalpy, would be the change of energy, and the change of pressure and volume. So this is really important if you are working with gases. It's not important if you're working with volume, or if you're working with solids and liquids. So if you're working with gases, you have to take into account the pressure and the volume. You know, especially the volume of a area of gas, right? Because gas expands to large volumes. So the pressure that basically going on here, it shows here. Let me show you. So if you take this equation here, and you're working with solids or you're working with liquids, then enthalpy will just equal the energy. You don't have to worry about that, and that would be the equation. So the equation would end up being the change in enthalpy would be equal to the change in energy. And since in liquids and solids, the changes in volume is very negligible, and if the pressure is constant, then we don't have to worry. So basically, they need to tell you this. This equation is very important when you have to do with gases. And enthalpy has to always take into account pressure and volume where energy does not. Okay? It's basically what you need to remember for that section. Now you're going to have endothermic and exothermic reactions. And this is really important because remember we went over the conservation of energy and how energy in the universe is never created or never destroyed. And so that is so important, you know, so we'll find this in exothermic and endothermic reactions, you know, in chemical bonds and how they happen. It's just happened just the way, you know, God has it. So what are endothermic reactions? Well, an endothermic reaction, the word means absorbed into. So energy is absorbed into, and it's stored in those chemical bonds. An endothermic reaction, endo meaning within, so you know it's stored within, right? It usually produces a cold product, a cold reaction. It doesn't produce heat, it makes things colder. Just remember, endo is going to make things colder because energy is absorbed and stored in the products. So the enthalpy of products is going to be greater than the reactants. So but basically, the change in H, the change in enthalpy is going to be positive. So whenever you have an endothermic reaction, you're always going to know the change in energy is going to be positive. It's going to be a positive reaction. Pretty important to know. So you'll have an equation that says reactants plus heat equal, let me see if it goes up here. Right here it is. So you're going to have this equation, reactants plus heat, because you're putting heat into the reactants, and this is going to produce a product, and it's going to be positive. It's going to be cold because it's taking in this heat on this side. So, and it goes over, actually one of the samples that it goes over is if you take in ammonium nitrate and you mix this with water. So this is an endothermic reaction. So you're mixing this with water, and then you'll see that the nitrate is dissolved in 100 milliliters at room temperature, and then the temperature drops to near freezing. So this is how they do cold packs. So you have this this mixture here, and you have this cold pack, and and you break the cold pack and it mixes the ammonium nitrate with water, and then you turn into instant cold. So endothermics are usually instant cold, and they're positive. They're always positive. Remember that. They're positive in enthalpy, or enthalpy, right? So that H will be positive. The reactants have basically are storing the heat here. They're storing the heat to this point. As they store the heat, they're making the products cold. So that's endothermic. Exothermic would be just the opposite. So let's talk about exothermic a little bit here. So here's a picture of here's a scale of the enthalpy of when you're talking about enthalpy with the reactants plus energy and on the products. And this is what we're going to talk about here with, here we're going to talk about exothermic. So some chemical reactions release energy that was stored in the chemical. It's something, an exothermic reaction exits energy. So a lot of times you have a bomb going off, or fire going off, or explosion going off, or the temperature rises a lot more, because exo means exit, out of. So we're talking about exiting the energy. And some of these chemical reactions, they release a lot of energy. They're stored in the chemical bonds, and suddenly they just release energy. And this causes products to become hotter, not colder, like endo is colder, become hotter. And the change in enthalpy that I talked about is going to be negative, right? Because you're getting, negative means you're getting rid of energy, right? So the enthalpy of the products would be a different equation. Let's look at that equation on the next page. Exo meaning out. Here's a picture here. Energy is absorbed. Here's the picture. Oh, here's the picture of what I was talking about is endothermic reaction and how the energy is absorbed and then makes things colder. And if you want to figure that out, there's a picture of just what we described, because the temperature of the water drops from 23 degrees centigrade to 14. It goes down, it becomes colder. Whenever you have a colder reaction, you know that's it's endothermic, right? So let's go on to the next. Let's finish talking about exo right here. So here's the equation for exothermic. Remember, exo means exit and thermic means heat, exit of heat. Here's the equation. Now you have the reactants, and they are going to produce the products and release heat. So heat's going to be, in all this whole section, is going to be negative, because negative means you're getting rid of heat. That's exothermic. And so some of the examples that they have, it's going to be negative, of course. The examples there may be propane. You know how propane and oxygen come together and they start burning? That's the exit. They're getting rid of energy. And we're feeling the energy of the heat, right? And the heat is released, and it makes anything that glows, like glows, is releasing heat, and the temperature goes up. You have an exothermic reaction. There's a lot of exothermic reactions in the universe. Anything flammable or explosive or bombs, they're all exothermic reaction, right? So just to know that. So let's go on. Here's some, we're going to talk about specific heat in just a little bit. So on that table here, let's go up here first. Calorimetry is the measurement of heat. So you think of calories in this section, calorimetry. Well, anyway, heat, the thing to know about this, a basic question, you probably learned this in grade school, and you can learn it by just, sitting in your room, and seeing how heat flows. Heat always flows from hot to cold, right? That is a basic. When both objects are the same, they'll stay in equilibrium, but if there's heat, it's always going to flow from the hotter to the colder. And in this way, we can detect a temperature change because heat is flowing from hot to cold. Test question: how does heat flow from hot to cold? Okay, so there'll be basically, you'll have, the initial temperature and the final temperature, be able to subtract it, and you can see whether the temperature is negative or positive, being that final temperature to losing. And that's what it's kind of describing here. Heat flow is detected by a temperature change. And here you have a temperature change here from the final from the final subtracted from the initial, and you'll see what the temperature changes. The temperature decrease has a negative T, and an increase has a positive T. That's pretty self-explanatory there. So now let's talk about this issue, which gets a little bit more complicated, but it's actually pretty cool because it has to do again with, the universe. It's called specific heat. And some elements and some compounds, I should say, require very little energy to change their temperatures at all. And others require much. An example would be like water, and water changing and raising a temperature of 1 degree, and you take copper in that temperature to make 1 degree. And if you do that, you'll find that they have different, temperatures when they change their temperatures in their specific heat. So what is specific heat though? Well, specific heat, the definition of specific heat is the heat required to raise 1 degree centigrade, which is 1 degree centigrade of temperature. So you're going to have the specific heat able to, of that element, is going to be able to raise it 1 degree temperature if temperature, specific heat in mass is known. So you're going to know the mass. So it's important that you know the mass, and to know the temperature, specific heat. Those things are important when you have to do with specific heat. So here, let's read this. The specific heat of a substance is the heat required to cause a unit rise in temperature of a unit mass of the substance. So you have this here. Anytime you have C, that little C is going to mean specific heat. The Q, of course, is going to mean heat, right? And mass and temperature. So you have heat, mass, and temperature you have to know, and then you could find out the specific heat, right? And so they did this here with water as I went over to find out what the specific heat would be of water. And so typically the amount of heat is not measured directly, so you have to do it by temperature change, right? So I was going to specific heat of selected substances. So let's look at the specific heat of water. And it's going to be basically water at what? Raising 1 degree temperature, at that set mass. So we have the specific heat is required to raise 1 degree. It could be in Kelvin too, but Kelvin is 298 degrees and centigrade is just 1 degree. Those are equal in the temperature of a unit mass of a substance. So now we have this equation, but as they put this in here, they find the specific heat of each one. Carbon dioxide, gas would be 0.85. Let's go down to water. Liquid water is 4.18. Now, you can see the gases and liquids are going to be different in these. So this is where they calculate these out for you so you don't have to do all the work. So when you have a question, they'll usually give you the specific heat so you can find the energy. So to use this equation to find the specific heat, it says here, if the temperature change, specific heat, and mass of a sample are known. If you know the temperature change, and you know the specific heat, and you know the mass, then you can find that energy transferred by using this equation. Q, remember, Q would be that heat energy. It's going to equal mass, that's the grams, times the specific heat, which is going to be this table number, times the temperature. So it's not so hard if you use this formula. It gets really easy. And that's what science does a lot of time. Math is the language of science, right? So let's go to this example here. So we want to know how much heat is lost by a piece of copper with a mass. So we know the mass. And it cools from 95 degrees to 20 degrees centigrade. The specific heat of the copper is 0.38 joules, that's per gram per centigrade, over gram per centigrade. That's the way they measure specific heat. So we have the mass, we have the temperature change, and we have the specific heat. So we can find the amount of heat, right? We say the amount of heat, which would be Q, heat, equals mass. So we plug in that mass, which is 50 grams. We plug that in right there, 50 grams. And then now we plug in the temperature. Well, what temperature is it? Well, it's a temperature change. From 95 to 20 is a decrease in temperature of 75 degrees. So we went 75 degrees lower. So that's our temperature change. So we can plug that in. And then we plug in the specific heat. So we have mass, we have the specific heat, which is probably in the table there or up here, they gave it to us. And then the temperature change is a negative 75. So use your calculator in these. It gets kind of complicated, you know, in large numbers like this and takes a lot. So just use your calculator and you can figure out, you put in 50 times 0.38 joules plus minus 75. And so then in this point, you're going to find out that change is going to be negative 1425 joules, or you can say negative 1400 or joules, or you can change it to kilojoules, which would be 1.4 kilojoules. But let's go ahead. We're going to go with this. I just go with this number. Negative 1425 joules would be the answer of it. So, and you see how in this problem, it's going to be in joules because we got rid of grams here because there's a gram here and there's a gram in the diameter, so you can get rid of the gram. And we actually got rid of the centigrade because here's a centigrade here and a centigrade here, so we got rid of those values. And so all we left out in this whole problem is joules. So you can see how if you work that out that way, it's going to be in joules. All remember, heat actually is going to be measured in what? Not calories, joules, right? At least the scientifically. So calorimeters, or calorie meters, that's what I call them. What's a calorimeters? Well, basically a calorimeter is a device to measure heat flow. And it usually a lot of times changes color because you can see the heat getting hotter and it will change like maybe redder or a different color. So you can tell the heat change. And so it's usually a device with the that has the constant pressure from the atmosphere. So usually it's just heat is going to be the enthalpy is going to be reaction to just energy. We're not going to really deal with pressure and volume in these situations. So, but anyway, we have some calorimeters down here and they're measuring enthalpy, right? Measuring that energy of heat, you know. So, and here's some pictures of them, how they do it. Now, I'm not going to go over this whole thing because that'd be a whole another section in itself, but you can see they get kind of complicated, but how they're measuring the calorimeters, how they're measuring these. And they even have a way you can measure it just in this coffee cup calorimeter. And then this is a constant pressure calorimeter, and this is a bomb calorimeter. So just remember the calorimeters are a device to measure heat flow. So I'm not going to go clear into that, of course. So let's go on to the next page, and I think they give you an example. Oh, it's kind of important, this part here too. So right here it says, of course we know for the conservation of energy that heat loss is going to equal heat gain, or heat loss plus heat gained is going to equal 0. So we know that. So according to the law of conservation, we're going to know this. So we can rearrange this and make negative heat lost equals negative heat gain. And so they can substitute this by putting in the MC times temperature when you have this lost and temperature, and you're going to see this is going to be lost, is going to be negative, and that's going to be positive. So that's kind of important in some areas, especially some areas that when you're measuring basically the specific, when you're using specific heat, right? Specific heat being this C, will be specific heat. If any of the 5 of 6 qualities are known, the 6th may be calculated. This equation is often used to determine unknown specific heats. A measured quantity of substance in the question is known is in the temperature. Well, anyway, let's go on to the next, and I'm going to have examples of this. So, example 6.3. So they kind of went over that and trying to explain it, but let's go over example 6.3 here. So, I was looking to see if here I did. Okay. Find the specific heat. An experiment to find the specific heat of lead, 49.8 grams of lead at 100 degrees centigrade, was placed in a coffee cup and containing 75 grams of water at 21 degrees, and the final temperature of the mixture was 22.7. What is the specific heat of lead? And you have to assume that no heat is lost to the calorimeter. So, okay. So, to the surroundings of the calorimeter. So, let's go on saying, well, the hot lead gives up heat to the cool water until both temperatures are the same, right? So, basically we have the heat of lead plus the heat of water is going to be 0. That means 0 means they're in equilibrium. Thus, you can fill in this blank here and put in the specific heat of lead, and you can put in the specific heat of water. So from this data given, you can just plug in the blanks, right? So you're plugging in the blanks. You have you're going to have the mass of the water. So we're going to do the water first, or wait, they're actually doing the water first, right? Because 22 degrees. Let's see. Let me see. We'll go back up to this question here. 22 degrees center is the final temperature. So we want to find the final temperature. This is the final temperature of PB is lead. So we have 22.7 degrees minus 100 degrees because it started at 100 degrees in our equation, right? So we have minus 100 degrees, and this is going to equal negative 77.3 degrees. Okay, this is the lead, right? So if we take 20, so we have 22 minus equals 77. So this is going to be our change in temperature of the lead. Now the mass of the lead, we already are given up here, is 49.8. So that's the mass of the lead. So now we're going to do the same thing for the water because it's going to involve the water. So we have 22.7 degrees centigrade minus 21 of water, and the water change of temperature is going to be 1.7. And so now you have this water being 75 grams, which we got up here. 75 grams is going to be the mass. And then you have the specific value, or I should say, the specific heat value of the water we know is 4.18. We can get that from the table. I don't know if it says up here, but you can get that from the table and you know that specific heat. So now you know this whole equation. You know what the mass is, you know what the specific heat, you know what the temperature is. So we have all these here. And so then we're going to solve this problem by plugging it in to here. You know, basically this section here. So you're going to have one being negative and one being positive, right? So this section here, negative Q lead equals positive Q water. So we plug that in. It kind of looks complicated, but if you just plug in the numbers, it's so easy, and put it in your calculator, you know. So here here's our equation. We have the equation of specific heat. You have the specific heat here of the water divided by that of the specific heat of the lead, and you fill in all these blanks, and what do you get? You get the specific heat of lead to be 0.138 joules per gram per centigrade. So this is when you want to find out specific heat. But the thing about this whole thing is that you can now look in tables and they'll just tell you what specific heat. You don't have to figure this whole thing out. But this is how they figured it out. Okay? So the last part here heats the reaction. Let's see. We're going to learn about the heats of the reaction. Well, what's the heat of the reaction? So this is where you're going to use balanced chemistry equations. Don't let that get you out of whack either, because it's kind of fun using balancing equations, and we actually can find the heat of a reaction of molecules, which is really amazing. So the heat of reactions used balanced equations to determine the heat liberated or absorbed in a reaction. And this is called the heat of reaction. The total amount of heat liberated or absorbed, start to the end, is the heat of reaction. So heat of the reaction is that liberated, the heat liberated. So here we have up here, see here, the equations they used here. So they have two equations. We're representing this. We're going to represent this as, it says, when 2 moles, whenever you have a 2 in front of that, remember that's moles, we have 2 moles of hydrogen gas, and it's reacting with oxygen, and 1 mole of oxygen actually, and then it will produce 2 moles of water and heat, and that's how much heat. So that's what we have. So we know, we may represent this in this equation, right? And so we'll know basically here, again, that the 2 moles of hydrogen and the oxygen are producing this liquid water. that this enthalpy change, this heat change is going to be negative, because basically what's going to happen, the heat's given off in an exo, it's going to exit, and exits are always negative. You're getting rid of heat, right? So the coefficients are the mole amounts. So we know that the coefficient is basically going to be that number that's before the H right there. So the coefficients, there. So let's go on here. Let's go down here. So you can see also this equation here basically is the same equation as here. They just divided everything by 2, got rid of that 2 and put a half. So they can have this equation here. So thus every mole, they want to know 1 mole, we have to divide it by 2 because there's 2 moles. So if we want to know 1 mole, we have to divide it by 2. And so we divided the whole equation by 2, and you get 286 kilojoules, negative 286. They just divided to get rid of that 2, right, into this equation. So, and we can't measure enthalpy in absolute terms, so we have to measure them whether by temperature and such, right? By outside sources. So I like this part where it says the height we give depends on the reference point. So this is what we talked about in the last section. We're talking about that standard state. So the reference point chosen for enthalpy is the enthalpy of uncombined free element in its normal state at 1 atmosphere, 290 K, which would be 1 centigrade. K is Kelvin, 290 K, and that would be its physical normal state. That's why we're taking in account pressure and volume. And this arbitrary assigned problem 0. Thus, any element in its standard state has assigned enthalpy of 0. Kind of important. Any element. So an element, oxygen, just oxygen, if it's on the periodic table, it's oxygen, iron, hydrogen, helium. They're all going to just have zero enthalpy. But compounds will have, any compound will have a specific heat. So no specific heat to elements, only to compounds. So here's an analogy between this enthalpy and the high mountain. So we have a high mountain, 12,000 feet height from the base of the mountain right here. So if we're just measuring this much, we get 12,000 feet. Oh, but we decided we're going to measure from sea level, and it's 29,000 feet from sea level. So it's really important that we have a standard where we're measuring from. That's the standard state. And this table, so if you're going to go by this table is basically all, as you can see here, all of the standard enthalpies or the specific heats there. So when you need to know the specific heat, this is enthalpy of these things, an element. These are all weird, these are all different. I say weird elements, they're all not elements, they're compounds. So they all have, remember, an element always has 0. And a compound will have that enthalpy state. So if you have, let's go for H2O. H2O water is going to be negative 285.8. H2O of gas is going to be negative 241.8. And so you have, those are 241.8, 285. See how they're different? They're different in their liquids or gases or solids. So there's a lot of states. If you say magnesium oxide, or you say sodium chloride, or you say ammonia, or all these, you look up their formula in here, and then you can look up the enthalpies it says 25 degrees centigrade in 1 atmosphere. Okay? So they're measuring them at that standard state. That's that. So in your problems, you're going to have to go back to this table. They'll always say, go back to table 6.2 on this compound. Remember, elements are always 0, but these compounds always have a standard enthalpy to give, right? So in this question here, or this area here, we have an exothermic reaction. Remember, when things are exiting, exothermic reaction is basically the enthalpy is getting, basically you're getting rid of energy. Endothermic reaction, you are taking the endo within energy of reactants and products and exothermic reactions there. And they're talking about this one's talking about oxygen. And anyway, they have these reactions and they talk about, and you'll see. And this has nothing, they're not really measuring temperature in this, they're measuring enthalpy. So Because temperature would be almost opposite. So let's go. Okay, I'm going to stop there. We're going to finish this up because I have to finish the questions too. This is kind of a longer section, so.